In this video, I want to have a bit of a closer look at curve sketching. So when we've looked at sketching curves before, we've had sort of this toolbox of things that we look for. So we look at the domain, we look at symmetry, so whether it's an odd or an even function. We're looking for the x and the y intercepts, and we were looking for asymptotes or limits. But now that we've started looking at derivatives and how they relate to curves, we've also got these 2 points here. So we can look for stationary points of a curve, and we can look at the concavity of the curve and whether there's any points of inflection. So let's have a look at how we can use those in an example. So our example asks us to sketch the function f of x equals x over x plus 3, x minus 3. So we're going to go through that checklist and have a look at all those different things that we had listed just then. It doesn't matter what order we do it in as long as we do each one of them. So let's start off with the domain. So the domain is all the values of x that can satisfy that function can take on. So if we have a look at this, because we've got a fraction, we know that the denominator of a fraction can't be 0 because we can't divide by 0. So that means that x cannot be equal to minus 3, because if it was, that first bracket would be equal to 0. And it can't be equal to positive 3 because the second bracket would be 0. But any other value of x that we put in there will work. So our domain is x cannot equal 3 and x cannot equal minus 3. So what it means is that at those two x values, we actually have asymptotes. So that's going to come in handy in a little while. All right, the next thing we can have a look at is symmetry. So we're looking to see if it's an odd or an even function, or it might not be either. So we're going to find f of minus x. Now when we do this, we're trying to figure out if it comes back to be the exact same equation, or if it comes out to be negative of this function. So we're going to put a minus x in there. So we'll have minus x over minus x plus 3 minus x minus 3. Now in the denominator here, we can pull a negative out of each of those brackets. So we'll leave our minus x on the top. If we pull a negative out of the first bracket, we'd be left with x minus 3. And if we pull a negative out of the second bracket, we'd be left with x plus 3. Now that minus that we're pulling out, I'm going to put that at the start as well. We'll be left with x plus 3. And that minus minus is going to cancel itself out. So we're going to have minus x in the top still over x minus 3, x plus 3. Now if we compare that to our original, we've got an x minus 3 and an x plus 3 in the denominator, even though they're backwards. But instead of an x, we have a minus x. So that means that this is equal to minus f of x, which means therefore it's an odd function, which means it has rotational symmetry about the origin. All right, next let's find our intercepts. So to find our x-intercept, we're going to set y or f of x equal to 0. So we're going to have 0 equals x over x plus 3, x minus 3. And the only way that that can be 0 is if our numerator is 0. So that's going to give us x equals 0 as our x-intercept. For our y-intercept, we're going to set x equal to 0. So we're going to have y or f of x equals 0 over 0 plus 3, 0 minus 3, which is just going to be 0. So our x-intercept is x equals 0, y equals 0 for our y-intercept. What do we want to look at then? We can look at our asymptotes and limits. So we've already figured out that we have two asymptotes, one at x equals 3 and one at x equals minus 3. But let's have a look at the limits as to what's happening to the function as x gets really, really big, either in the positive or the negative direction. So let's find the limit as x approaches infinity of our function. So if we expand out that denominator, that's going to give us the limit as x approaches infinity of x over x squared minus 9. Now, if we're subbing infinity in there, we're going to end up with infinity over infinity, which doesn't make sense. So we're going to go through and divide everything by the highest power of x in the denominator, so that x squared. So we'll have the limit as x approaches infinity. So x divided by x squared would leave us with 1 on x. X squared divided by x squared gives us 1. And 9 divided by x squared would leave us with 9 over x squared. Now we know that the limit as x approaches infinity of these two terms here, they approach 0 as x approaches infinity. So this limit is going to be 0 over 1 minus 0, which would just give us 0. So as x approaches infinity, our function approaches 0. Now we could go through and do the whole thing again for x approaches minus infinity, of x over x plus 3, x minus 3. And that's going to give us exactly the same, working out exactly the same thing. So we'll still end up with 0. So as our x gets very large in the positive and negative direction, our function approaches 0. All right, now I've had to rub that out to make some room. So I've just summarized what we figured out so far. We know our x and our y intercepts. We know that it's an odd function. We know that we have asymptotes at x equals plus and minus 3. And we know that as x approaches positive and negative infinity, our function approaches 0. So now we want to have a look and see if there's any stationary points. And if they are, we want to figure out where they are and what type of stationary points there are. So our stationary points, we're going to figure that out by finding the first derivative and setting that equal to 0. So before we find the first derivative, I'm just going to rewrite this as x over x squared minus 9. So expanding out that denominator. So now we can differentiate using the product rule. So that means our u is x, that numerator, and our v is x squared minus 9. So differentiating those would give us 1 and 2x. So our product rule, we're going to have v times u dash. So 1 times x squared minus 9 is just going to be x squared minus 9. Then we're going to have minus u times v dash, so 2x squared, over the denominator squared, so x squared minus 9 all squared. So simplifying that, we would have minus x squared minus 9 over x squared minus 9 squared. And if we pull out a negative there, we can pull a negative out of the whole thing and have x squared plus 9 over x squared minus 9 squared. So that's our first derivative. We want to set that equal to 0. So we're going to have minus x squared plus 9 over x squared minus 9 squared equal to 0. The only way that can happen is if our numerator is equal to 0. So x squared plus 9 equals 0. X squared equals minus 9. But we can't take the square root of a negative number, so that's going to mean that we have no real solutions to that, which means we have no stationary points. Okay, the last thing we want to do is check to see if there's any points of inflection, and then we can have a look at the concavity of our curve as well. So to do that, we need to have a look at our second derivative. So our second derivative, we're going to let u equal that minus. Now that minus is out the front, so if we attach it to this numerator, we're going to have minus x squared minus 9. And our v will be our x squared minus 9 squared. So differentiating those, we would end up with minus 2x. And differentiating this one, we'd have to use the chain rule. We'd end up with 2 outside of x squared minus 9. So it's differentiating the outside. And then the derivative of the inside is 2x. So we would end up with 4x outside of x squared minus 9. So putting that all in our product rule formula. So we're going to have v times u dash. So we'd have minus 2x outside of x squared minus 9 all squared. So that's v u dash minus u v dash. So that's this bracket and this bracket. So we're going to have minus x squared minus 9 times 4x x squared minus 9 all over that denominator squared. So we're going to have x squared minus 9. It was already squared, so if we squared a squared, it's going to become a power of 4. So we want to make that look a little bit nicer, so we'll leave that first term as it is. But this next one, I'm going to pull that 4x to the front. I'm also going to pull out a negative from this bracket here. So pulling out a negative would make this x squared plus 3, and it would also make this negative into a positive because we'd have negative, negative. So we're going to have positive 4x, and then this bracket became x squared plus 9, and we've still got our x squared minus 9 there, all over that same denominator of x squared minus 9 to the power of 4. Now all of our terms have an x squared minus 9 in there, so we can cancel one of those out everywhere. And we're going to be left with minus 2x outside of x squared minus 9 plus 4x outside of x squared plus 9 all over x squared minus 9 to the power of 3. Now in that numerator, I'm going to pull out a common factor of 2x, which would leave us with a minus x squared. And a minus 9 would give us a plus 9. And then over here, we're going to be left with plus 2, because we pulled out the 2x. So 2, and then expanding that out would give us 2x squared. And then 2 times 9 is 18. And we've still got the same denominator. And then just simplifying what's in the brackets, we'd have 2x outside of minus x squared plus 2x squared would be x squared, and 9 plus 18 is 27, over x squared minus 9 all cubed. All right, so we've found our second derivative. Now we need to know what to do with it. I'm just going to rub this bit out to give us some room. All right, so if we want to find points of inflection, then we need to set this equal to 0. So we're going to have 2x outside of x squared plus 27 over x squared minus 9 cubed equals 0. The only way that can happen is if our denominator is equal to 0. Sorry, our numerator is equal to 0, which means that either x has to be equal to 0 or x squared plus 27 is equal to 0. But if we rearrange that, would have x squared equals minus 27, and we don't know that that doesn't have any real solutions. So we know that we're going to have something happening at x equals 0. Now to test what's happening at that point, we're going to have a look at the value of the second derivative on either side. So we've just rewritten, we've got our second derivative here. So we're going to draw up a table of values. So our point that we want to test around is at 0, and we know that our second derivative is 0 there. So we want to test either side, but we've just got to be careful not to go past those asymptotes. So let's try minus 1 and 1, and that'll tell us what's happening about that point, whether the concavity is changing. But while we're at it, we may as well also test the other regions, so on the other sides of those asymptotes. So let's test minus 4 and 4 while we're at it. So we're going to go through and put all of those values into this function to find those values down there. So once we've got those, we can interpret them. So we know over here it's concave down, concave up, concave down, and concave up. So we're looking at the negatives and the positives there. So now we have all of our information, we can start actually trying to sketch our function. Okay, so all the time we're doing this, we want to be keeping in mind that our function is odd, so it's going to have rotational symmetry. So we know that we have an x-intercept and a y-intercept at the origin. So our curve is going to pass through here. We know that we have asymptotes at x equals plus and minus 3. So at 3, we can draw in our asymptote. And again, you should be using a ruler for these. Right, so we've got our asymptotes in there. So our line's going to approach those but never actually touch them. Now what we have to do is figure out what our function's doing in those 3 sections. So we know that there's no stationary points. We know that on either side of this, we've got a concave up and a concave down curve. So that means that it's going to be concave down here. Oops, change it back to red. Concave down here and concave up here. So we can see that our curve's sort of going to come down like this. We also know that as x approaches infinity, our function approaches 0 but never actually touches it. So we've also got a horizontal asymptote in these sections where it's not going to cross that axis. Now, if we combine that with these concave up and down sections, we can figure out where our function is in here. So let's draw in this middle section first. We know that this one's going to come down this way. This one's going to come up here. So it's approaching those asymptotes, but it's not actually touching them. Now in this section, when x is greater than 3, we know our curve is concave up. So if our curve is concave up, it can't be below that axis because eventually it would hit it, and we know it doesn't. So concave up, and we know that it approaches 0 over here. So that means it's going to look a bit like a hyperbola. And then over here, we know it's concave down, so we're going to have the opposite. And also, once we have this, we can sort of see what it's going to look like because we know it's got that odd or rotational symmetry. If we have a look at that when it's drawn by a computer, we're pretty good. We've got that point of inflection here. We had our asymptotes at -3 and 3. It's just a little bit neater. So that's having a look at the tools we can use to sketch a curve.